G'day, we're Monash and Rover, a multidisciplinary student team of over 100 members based in Melbourne, Australia. Our Rover Banksia returns for URC 2026 with interchangeable arm, science and autonomous payloads to tackle each mission requirement.
Banksia's core mechanical systems are designed to reliably handle the harsh, rocky terrain of NDRS. For robust traversal of tough terrain, the chassis features an in-house designed and manufactured 15:1 cyclodal drive gearbox, capable of maintaining 3.6 meters per second with 32 Newton meters continuous torque to navigate over rocks, debris, and other difficult obstacles. Precision-controlled 70:1 reduction pivot modules allow 360-degree on-the-spot pivoting and a variety of turning options for a precise operation, critical in aligning the competition payloads.
To support the drivetrain, our flexible TPU wheel treads fit with our custom bike spoke wheel geometry, offer reliable traversal over a broad range of terrain. The four-wheel rocker planar suspension enables Banksia to climb and descend steep slopes whilst providing stability for transporting objects and payloads for all tasks.
Banksia is powered by the Jetson Orin Nano connected to our returning custom carrier board, providing the necessary processing power for the URC missions. To tackle the extreme heat in a competition environment, we designed a new fan card to conduct active cooling within the chassis, while continuously monitoring heat dissipation from our voltage regulator boards.
Our main power delivery is supported by our bespoke Lyro battery unit equipped with an emergency stop, cell balancer, and bidirectional power control for safety. Notably, our radio signal integrity is improved by the adoption of a patch antenna array coupled with the steerable directional Yagi transmitter. This provides a minimum 1 kilometer range and sufficient bandwidth for the delivery mission.
Upgraded camera feeds, motor telemetry and payload sensors are streamed to the base station and displayed on our custom graphical user interface. Operators use the GUI, a gamepad controller and joysticks to control the rover. RTK differential GPS allows centimeter accurate manual and autonomous navigation up to distances of greater than 1 kilometer.
Helping Banksia, we have our quadcopter Rosella. Rosella uses ArduPilot to autonomously fly to areas of interest with minimal operator input, aiding the rover operators in the delivery mission, while a 4K FPV camera and goggles allow small features such as sign and debris to be identified.
This year, Rosella communicates with the base station via a Aveline connection, providing real-time system status updates and allowing GNSS coordinate waypoints to be modified live.
Our new robotic arm type band features 6 Revolute joints, providing the dexterity, strength, and precision required for both the equipment servicing and delivery mission. The parallel bar linkage mechanism shifts the center of mass towards the base, reducing motor torque requirements and allowing the arm to lift loads exceeding 5 kilograms.
Type band is driven by brushless DC motors and equipped with incremental and absolute encoders, enabling both velocity and position control. This, in combination with our newly integrated differential wrist, allows for precise interaction with elements such as switches and buttons, as well as placing the case in the drawer, inserting the USB cable and the fuel hose to the Landau.
Our new Inverse Kinematics plugin and digital twin have been developed for intuitive control of typeman. Autonomous typing software locates the keyboard visually using Orica tags and edge detection of the required key. Then, our custom pathing library and IK plugin are leveraged to move the end effector smoothly to the target key.
Our 2026 URC science payload features integrated subsystems to streamline sample collection and analytical processing. Sites of interest are selected using a digital microscope, alongside a non-invasive near-infrared reflectometer, designed to survey sites for nitrogenous bases. A 360-degree camera captures panoramic photos to document site context and stratigraphic profiles. Our auger assembly uses a Hall effect sensor to collect regolith from below 10 centimeters, with samples stored and sealed in removable caches. Probes are used to record sample moisture and temperature.
Transported by peristaltic pump, samples are heated and subsequently analysed via a custom UV visible spectrometer. Cuvettes containing anhydrous and molasses reagent react in the presence of amino acids and carbohydrates, with near UV fluorescence being measured for UV excited NADH. The intensity of the return spectra can be used to quantify these biosignatures. A custom litmus array reveals sample properties such as pH and ammonia concentration.
Our autonomous stack continues to utilize and extend the Nav2 framework developed by Open Navigation, giving us a solid foundation for features such as path planning, obstacle detection, and decision making.
This year, our sensor suite consists of a GPS, LiDAR, all cameras, IMU, and wheel encoders. With EKS sensor fusion, they allow us to localize the rover to perform necessary tasks.
For path planning, Nav2's Navifan Planner was chosen as the paths it generates are sufficient for traversal over long distances.
Obstacle detection uses Nav2's voxel layer from Cosmap 2D with processed point clouds from the LiDAR as a source.
For decision making, a custom behavior tree directs the rover to navigate towards areas of interest, performing actions such as searching the area for an object and stopping at said object when found.
Objects are detected with a YOLO V8 nano model and localized by calculating the distance from the object to the camera to a depth image.